G'day, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics tutorial video. Today I'm going to go through looking at how we take a system of forces and moments. So in this problem it's just forces, and how we find an equivalent force and moment at a location, and then we find an equivalent just a single force with no moment at some other location. So I'll just share my screen and we'll get started with the problem. Okay, so here's the problem that we have. So in this problem we've got a beam simply supported at each end, but that's not important for this particular problem. What is important is the fact that we've got two forces here and we've got the locations of those forces, and the problem is to determine the x and y components of the resultant force and specify the distance where this force acts from point O. The way we normally deal with these problems is to go through another step first, and that is to find the equivalent single force or the equivalent components of a force at point O and the associated couple or moment, and then find the equivalent single force that would replace the force and the moment at point O. So it sounds a bit abstract, and it kind of is in this kind of a problem. But I've got another problem coming up a bit later, which is a little bit more practical. But anyway, this is a simple problem to get us started with. So we don't have to worry about, in this case, x components, because well, depending on how we define x and y, but let's assume we define x as horizontal and y as vertical. We've only got y components to worry about. All right, so let's work through the problem and see how we go. All right, so our solution will be to first, as I said, determine an equivalent force and couple at point O. All right, so how do we do that? We'll see in a second. And then once we've done that, though, as I said in the introductory blurb, we then use the moment equation to determine where the resultant acts. So the thing that's being asked for in the question as written, this is what we use to determine that. All right, so let's start with calculating our resultant forces first. So we only have to worry about vertical direction in this case. So our resultant in the vertical direction, this is sum of the forces in the vertical direction, and hopefully you can see that pretty easily, is 460 newtons, so we just add the two up. Now we want to calculate the moment effect of those two forces about point O. Hopefully we remember our moment equation, force times the perpendicular distance, and the rest of the sentence, which is perpendicular distance from the point that we're calculating moments about to the line of action of the force. Right, so in this problem it's pretty obvious. Right? So to the 200 Newton force it's going to be 2 meters, and to the 260 Newton force it's going to be 4 meters. Right, so let's put that in. And firstly, I'm going to assume, in this case, clockwise is positive. In most of my videos and examples, I assume anti-clockwise is positive, but this time I'm going to assume clockwise is positive because I can see pretty obviously that these two forces here are going to cause a clockwise rotation. So it just makes dealing with the signs a little bit easier. So the first one, 200 times 200 times 2 meters. So this little dot here means multiplied by, not 200.2. And then plus 260 times 4. And we get a total net moment of 1,440 Newton meters. All right, so we can represent that on a diagram. So we can show our resultant force R there, and a moment M subscript 0 at the location 0 that we've identified. Okay, so what we have here is that this is equivalent to this loading. Okay, so if we have a force here, a 460 Newton acting downwards, and a moment here clockwise of 1,440 Newton meters, this loading is equivalent to these two forces here, but only on the external effects on the body. Okay, if we're interested in the deflection or internal effects such as the deflection and stresses in the beam, they're not going to be the same. But the external effects of these two force and moment systems are equivalent. So if we did an equilibrium problem and solve for the reaction forces at these supports, if we do the problem with the forces applied like this, we would get the same answers for the reactions at the supports as we would if we had a force applied here and a moment applied at point O. Okay? If you know how to do rigid body equilibrium problems, have a go at doing that and see what you get. All right, so the next part of the problem is, now that we've got a force and a moment here, right, the question says, determine the resultant force and specify the distance where this force acts from point O. So what we want now is just a single force that's equivalent to these two original forces, and of course also equivalent to what we've just calculated, the single force and couple moment at point O. Location of the single equivalent force R should be such that it produces the same moment m0 about point O. Right, so can you guess or approximate where that force should be? Let's draw some forces. So I want to know a single force that's equivalent to those two original ones. So we've got one here, say, one here, or one here, or one here, or even one here. So let's label them 1, 2, 3, 4, 5. All of them are equal to 460 newtons. Where do I need to place that 460 newton force in order for it to be equivalent to this loading and also equivalent to this loading? So clearly this one's not going to be right. It's not going to be number 1. What about number 2? I'm pretty sure you can see that if we put 460 newtons here, it's not going to have a big enough moment. It's not going to be 1,440 newton meters. If we put it out here, or even out here, you can see it's going to be too big, right? So I think hopefully you can see that it's going to be somewhere between these two original forces. So let's get rid of all of those now and see what we get by going through the calculations. Right, so we want it to be somewhere there. Right? So we need to guess approximately where it is. So we previously calculated this force R. Now we want the location of this force to be such that when we calculate its moment about point O, it has this value. Okay, so the same value of MO that we calculated before. So we know this value MO, 1440. We know the value R, 460. So the thing that we don't know is D. So we just need to rearrange that equation and solve for that distance. Okay, so do that maths and we get 3.13. Okay, so we can see that it is between the two forces and a little bit closer to the larger of the two forces. Okay, again, which you might expect. All right, so did you guess where the force would be? All right, so that's the end of the problem. Hopefully that was helpful and instructive for you. All right, so that's it. See you for now, and I'll see you in the next video. Bye.